Let's now examine the borehole environment, looking down at a horizontal section of a borehole drilled through a permeable water-bearing formation. Mud filtrate is forced into a permeable formation by the pressure differential between the mud column and the formation. This forms a solid mud cake on the borehole wall. The mud cake usually has a very low permeability, and once formed it reduces further invasion of the mud filtrate. Adjacent to the borehole, most of the original formation water and most of the hydrocarbons, if present, may be flushed away by the filtrate. This zone is known as the flushed zone. Farther from the borehole, the displacement of the formation fluids is gradually less complete, resulting in a transition zone between mud filtrate saturation and original formation fluid saturation. This zone is known as the transition or invaded zone. The extent of the flushed and invaded zones depends on many factors, including the nature of the drilling mud, the formation porosity and permeability, the pressure differential between mud column and formation, and the time since the formation was first drilled. Generally, very porous and permeable formations are seldom deeply invaded. This is because initial rapid invasion causes an impermeable mud cake to quickly develop. Here we see some common symbols used in formation evaluation. The resistivity of the mud is referred to as R sub m. The resistivity of the mud cake as R sub mc. The resistivity of the flushed zone as R sub xo. The resistivity of the mud filtrate within the flushed zone is referred to as R sub mf, and the water saturation in the flushed zone is referred to as S sub xo. Remember, when using these symbols, the flushed zone is referred to by the subscript xo. The resistivity of the transition zone is referred to as R sub I. In the uninvaded zone, the true formation resistivity is referred to as R sub T. The resistivity of the water is referred to as R sub W, and the saturation of the uninvaded zone is referred to as S sub W. A common case is where a borehole with freshwater mud penetrates a water-bearing permeable formation containing saline formation water. Thus, the resistivity of the mud filtrate, R sub mf, is greater than the formation water resistivity, R sub W. A profile of resistivity outward from the borehole, in this case, shows the presence of mud filtrate, causing a high resistivity in the flushed zone, R sub xo. Resistivity then gradually decreases in the transition zone until it reaches R sub T, the resistivity of the uninvaded zone, which is low due to the presence of saline formation water. The symbol R sub O is used to denote the resistivity of a formation which is 100% water wet. Thus, in this case, R sub T equals R sub O. The resistivities of the mud, R sub M, and the mud cake, R sub MC, are also low compared to the resistivity of the flushed zone. This resistivity profile also assumes freshwater mud, but in this case, the formation is a permeable oil-bearing bed. The resistivity of the flushed zone, R sub XO, is high due to freshwater mud filtrate, as was the case in the previous profile. The invaded zone has a mixture of mud filtrate, formation water, and some residual hydrocarbons. Such a mixture causes high resistivity, in some cases equal to that in the flushed zone. Sometimes in hydrocarbon-bearing formations, the mobility of the hydrocarbon is greater than that of water. In this case, an annular zone, R sub AN, with a high formation water saturation, may be formed between the invaded zone and the uninvaded zone. Thus, this annular zone, if present, may show up as a zone of relatively low resistivity. Because hydrocarbons are highly resistive, their presence in the uninvaded zone causes higher resistivity than if the zone contained only saline water. The resistivity of this hydrocarbon-bearing uninvaded zone, R sub T, is normally somewhat less than the resistivity of the flushed and transition zones, which contain freshwater mud filtrate.